Morning everyone, I am Shantanu Pathak and today I will present my work on strain and field tunable non-relativistic spin splitting and wave symmetry dependent spin transport in twisted bilayer altermagnets. So this is the outline of my presentation. Firstly, we will see why we need spintronics over electronics, because in electronics there is only one degree of freedom, which is a charge. Due to this electronic motion, there is joule heating, high power consumption, and scaling limits of the devices are the one of the main disadvantage of electronics. So we add a additional degree of freedom, which is a spin. When we include it, it enables low power consumption, high speed, non-volatility, and the device has long spin lifetime. So this is the schematic of Rashba-Uralson effect, in which we have generate spin polarized current using the charge current. But most of the spintronics is studied with spin orbit coupling effect, but it has some limitation, like strong SOC require heavy element, and spin dephasing is one of their limitation. So we need to generate spin polarization without spin orbit coupling effect. So in non if a system is non-magnetic, there is a time reversal symmetry is preserved there, where we can observe that if time reversal symmetry is preserved, then spin degenerate bands are there. So we need to in order to get the spin splitting, we need to break the time reversal symmetry. So we induce the magnetic ordering in the system, and we know there are two type of magnetic ordering: ferromagnet and conventional antiferromagnet. We induce and these days, another magnetic ordering is also there. It is called altermagnets. Ferromagnets and conventional antiferromagnets, we all know that ferromagnets are when in which spins are aligned in one direction, and antiferromagnet spin are aligned in such way to get the total magnetization zero. Ferromagnet has advantage, like we observe the spin splitting, but it has disadvantage that it has some net magnetization. In antiferromagnet, it has net magnetization zero, but we observe the spin degenerate band, and with spin degenerate band we observe no spin transport. But in altermagnet, spin alignment is same as AFM, but the opposite spins are opposite spin sides are different symmetry projected. So it has net magnetization zero, and we observe the momentum dependent spin splitting, which is purely due to the crystal symmetry, not depends on the spin orbit coupling. So altermagnets had advantage, like we observe spin splitting, zero net magnetization, zero stray field. So we use this for our study. These are the applications of altermagnet. Like we can generate longitudinal transverse spin current. We can also make the device with giant magnetoresistant. We can study the spin splitter torque. In our study, we have studied the spin splitter angle, which is simply a ratio between the spin conductivity and the charge conductivity in the twisted bilayer system. Now we will see what are the twisted bilayers. When two atomic layers are rotated relative to each other, it forms some patterns, like we can see here. Some patterns are forming. These patterns are called Moire patterns, and on which angle we have observed these patterns are called twist angle. Twist angles modifies the electronic and magnetic properties. This is why it is provide a potential platform for altermagnetism, and with interlayer control due to the symmetry breaking. Now comes to the result and discussion part. We have studied the twisted bilayer in square and hexagonal type, where this is the example of systems we have studied in twisted bilayer, and this is the crystal structure of the twisted bilayer for square lattice type and hexagon lattice type. Now comes to the electronic properties calculation. Like in this system, hexagon has this Morley-Brillouin zone where the high symmetric path is gamma mk gamma, and the square lattice has gamma xm y gamma. We can see here. So when we plot the spin bands, when we plot the spin polarized band structure, and we have observed at CBM and the VBM, and CBM and VBM of this hexagon and square lattice, the spin degenerate bands are there. So there is no spin band degenerate bands are there just due to the spin sublattice symmetry. So we have projected that we will study this K1 and K2 path, and M1 to M2 path for the hexagon, and X to Y path for the square lattice for the non-relativistic spin splitting. And we have succeeded, and we have observed this non-relativistic spin splitting on this high symmetric, on this generic path. But these points are high symmetric. Now we have, in order to get the spin splitting parameters, we have fitted it with the K dot P model Hamiltonian. Due to the time constraint, I will not go into depth. This is the effective Hamiltonian we have observed via using this symmetry analysis approach, and where this alpha 1 is linear spin splitting coefficient and this neta is cubic spin splitting coefficient, and we fitted it with the DFT data, and we have observed a finite non-relativistic spin splitting coefficient of the order of 1120, which is electron volt angstrom. So it is quite comparable to the Rashba splitting. Now we will see what are the type of ultramagnets are there. So we have plotted the spin splitting wave texture, in which it is simply a kx ky contour plot, where the red color denotes the spin up contribution is higher and blue denotes the spin down contribution is higher. So in our systems we have get this D, G and I wave type ultramagnets with a finite spin splitting energy, which is 60 MeV in the twisted bilayers. Now we will see what is the effect of electric field in the system and strain in twisted bilayers. When we apply the electric field, it breaks the spin sublattice symmetry, and it intro- it introduced the system with Zeeman-like interaction, and it breaks the spin sublattice spin degeneracy at high symmetric points. And we observed that the energy levels in this band structure, we can see this energy levels are split into E plus and E minus, while before this electric field it is degenerate. And where here delta is the just the difference between the up and down spin energy, and we have observed that when we increase the electric field, and delta also increases linearly. The same we have applied the biaxial strain in the system, since biaxial strain doesn't affect the symmetry. So but it also affect on the NRSS, and we have observed when we apply the compressive strain in the system, it increases, NRSS increases, and when we apply the tensile strain in the system, NRSS decreases. Same, we have applied a diagonal shear strain in the system, which is simply a tensile strain in x direction and compressive strain in y direction, where we have observed that G wave and I wave has this C4Z symmetry in G wave and C6Z symmetry in I wave. While we applying this strain, it breaks this spin it breaks this symmetry, and the system converted G to I and G to D and I to D in the system, and we have observed the same in our twisted bilayer for G and I wave, where the spin splitting energy is also increases with this uh, strain. The main reason why we applied this strain is because the G and I wave suppress the spin transport. To enable the spin transport, we applied this strain, and now they are converted to D wave, and D wave support the spin transport, which we have also validated via calculating the spin resolved conductivity in Boltzmann transport. This is for spin up and spin down channel conductivity formula, where total charge conductivity and spin conductivity is the addition and subtraction of this spin channels conductivity. And we have calculated this spin splitter angle, which is a simply transverse spin ratio of the transverse spin current divided by this longitudinal charge conductivity. And we have plotted with we have plotted it with the strained and unstrained system. Unstrained system is denoted by black color, and strained system is denoted by this red color. And we have observed that spin conductivity is enables, and spin splitting angle we have observed for the TbCO2 system is the order of 8 degree, and in MnTe2 system it is around 17 degree. So it is quite promising. So now comes to the conclusion part. We have observed a finite non-relativistic spin splitting of the order of 1 electron volt angstrom. We have get the ultramagnet with D, G and I wave, and it provides a tunability when we apply the electric field, Zeeman tuning. When we apply this strain, alpha 1 tunes, and also we can transform the wave symmetries. Due to this, it enhanced the spin transport with spin splitting angle around 8 degree and 17 degree for the TbCSUL2 and TBMNTA2 systems, and it provides the potential platform for the next generation spintronics device. With this, I will thanks. Thank you.
Thank you, Chandran. Yes, we can have one or two questions. No question. Maybe can I ask that how the measurement is carried out? I mean, it's Sir,
Sir, this is a DFT. Okay.
DFT1.
Yes, sir.
Okay. So, do you expect that this can be realized in near future? I mean,
Yes, sir. Because in recent years, many TMDs are realized in twisted bilayers. So I think just alternates can be.
because alternating is a new phenomena. I mean, lot many people are working on.
Yes, sir.
Look forward for alternate. Okay. Thank you.
Thank you, sir.